Welcome back, students. And with this video, we will start our fourth lecture, which will be dedicated to map projections and coordinate systems. I think you have some knowledge about this topic from the basic course of geography from school, but uh, probably some many things can be unfamiliar to you and also a little bit hard to understand. However, this topic is very interesting and also very important working with ArcMap, and I should know that even some professionals, or probably even many professionals, do not fully understand the concept of map projection and coordinate system because it's a very huge and long topic. But you will need the basic understanding of these concepts in this lecture during your work as a GIS professional. So let's start. So what is a coordinate system? Coordinate systems enable geographic datasets to use common locations for integration. A coordinate system is a reference system used to represent the locations of geographic features, imagery, and observations such as GPS locations within a common geographic framework. Coordinate systems and coordinate reference systems. A coordinate is one of the sequence of values describing a position. The sequence is sometimes called a coordinate tuple. Coordinates are referenced to a coordinate reference systems. A coordinate reference system is a coordinate system, an abstract mathematical concept without any relationship to a physical object that is referenced through a datum to the Earth or some other object such as vessel. So the coordinate reference, you should distinguish between coordinate reference system and a coordinate system. So these concepts are very familiar and sometimes used interchangeably, but there are some discrepancies between them, and I will explain to you the differences on this lecture on one slide. So let's go. So far, types of coordinate systems. So there are two types of coordinate systems: geographical coordinate systems and projected coordinate systems. Geographic coordinate systems are 3D, also called 3D coordinate systems, and units are measured in degrees, while projected coordinate systems are also called 2D or Cartesian coordinate systems, and units are meters measured in meters and kilometers. Actually, the real coordinate system is a geographic coordinate system. Well, for instance, we use them in a GPS, or in a navigation, all the navigation systems in your mobile phone, etc., etc. But as a GIS professional, you will mostly use projected coordinate systems. So projected coordinate system is derived from the geographic coordinate system during a process called a projection. Why we need the projected coordinate systems, I will explain to you. At first, let's start from the geographic coordinate systems. So the line of latitude midway between the poles is called the equator. It defines the line of zero latitude. The line of zero longitude is called the prime meridian. For most geographic coordinate systems, the prime meridian is a longitude that passes through Greenwich, England. All the countries use longitude lines that pass through Bern, Bogota, and Paris as prime meridians, but mostly almost all local and regional and global projections are based on the Greenwich as a prime meridian. So on the first image, you can see the equator. So zero equator, which divides our globe into south and north poles. And on the second image, you can see the prime meridian, which passes through Greenwich. This is a meridian of 0 degrees. And if the equator is 0 latitude, prime meridian is called 0 longitude. And they both create a graticular network of our Earth sphere. And if the latitude starts from 0 degrees and the maximum reaches the 90 degrees. The prime meridian starts from 0 degrees and reaches 180 degrees. Prime meridian divides our Earth into the Western Hemisphere and Eastern Hemisphere. So projected coordinate systems. If you want to produce a map of features on the Earth's surface, you need to transform the spherical surface to a flat map. This transformation from three-dimensional surface onto a two-dimensional map is called a projection. Projection is a process when you convert your sphere, in our case our globus, right, to a two-dimensional map through using several mathematical processes and taking as a basis a mathematical model of the Earth, which is called a datum. Projected coordinate systems. A projected coordinate system is defined on a flat two-dimensional surface. Unlike a geographic coordinate system, a projected coordinate system has constant lengths, angles, and areas across the two dimensions. A projected coordinate system is always based on a geographic coordinate system that is based on a sphere or spheroid. So we should understand that the actual coordinates are geographic only, while projected coordinates are derived from the geographic, but they always contain some distortions. Datums. A datum is an ellipsoid that is adjusted so that it matches the actual shape of the Earth of a particular region as well as possible. The datum serves as a 3D reference surface for calculating the geographic coordinates of a location. So our Earth is not a sphere actually. Probably because it's flattened during the poles, and as we see here on these images, right, and it's also it has more shape of an ellipsoid, and but also more correct and accurate representation of the Earth will be a geoid, but geoid is not a mathematical model. So therefore the mathematicians and the geographers created a mathematical model of our Earth, an ellipsoid, which is makes the best representation or approximation of our planet, but we can use several datums according to the region we're projecting, because some datums gives the best approximation on a certain area, while the others give the best approximation of the surface in other area. For the global projections, use it global ellipsoids such as VGS 84. So modeling of the Earth's surface. First, a mathematical three-dimensional reference surface which models the Earth's physical shape has to be defined, the ellipsoid. The ellipsoid is a smooth surface. The actual surface of the Earth represented by the mean sea level geoid is not smooth. This means that there are always discrepancies between the ellipsoid and the geoid. So even our geographic coordinate systems, and I'm not even talking about projected coordinate systems, has some distortions comparing to the real coordinates, because the real coordinates cannot be actually calculated, because our planet is not even an ellipsoid, and I'm not talking about a spheroid. It's a geoid which has the uncertain shape, and sometimes during the period it always changes, and geographers and mathematicians always create new forms of our Earth, new ellipsoids which give the best approximation in a certain region or in a certain time. Modeling of the Earth's surface. Since the space age, satellite-determined ellipsoids have become available that represent the closest fit of the entire Earth surface of the Earth. The most widely used ellipsoid is the VGS 84 because this is already the best approximation of the shape of the Earth. No adjustment based on the difference between the ellipsoid and actual shape is needed. So VGS 84 is mostly used for the global types of projections. Distortions. Map projections allow areas on the surface of the Earth's spherical surface to be represented on a map, flat surface. However, expressing a three-dimensional surface in two dimensions involves distortions of geometric properties such as shape, area, distance, and direction. So, when we make a projection of our geographic map, which are based on the longitude and latitude degrees, we lose one of these four characteristics, and our output projected map will store either a shape, correct shape of the country, or either area of the country, or the distance between the two points on, and or the direction. And only a few maps, a few types of projections can store at least two of these properties. No projection can preserve all these properties. Also, some combinations can be preserved, such as shape and direction, the Mercator projection. As a map maker, you must choose a map projection according to the properties you want to preserve in your map. This clearly depends on the purpose of your map. Types of distortions. Conformal projections. Conformal projections preserve local shape. To preserve individual angles describing the spatial relationships, a conformal projection must show the meridians and parallels intersecting at 90-degree angles on the map. Equivalent projection. Equivalent, equal area, means a projection preserves the area of displayed features. To do this, the other properties, shape, distance, and direction, are distorted. In equivalent projections, the meridians and parallels may not intersect at right angles. Types of distortions. And the third type of distortions is equidistant projections. Equidistant maps preserve the distance between certain points. Distance is not maintained correctly by any projection throughout an entire map. Distance is often only true when measures parallel to the meridians. True direction projections. True direction maps preserve direction, which means that direction measurements made on the ground are the same as direction measurements made on the map. Azimuthal projections are always true direction. Conformal projections such as the Mercator projection are also true direction. So, and the reprojection, the process of converting the map from one coordinate system to the other coordinate system is called reprojection. Reprojection can be two types. For instance, also reprojection can include the converting the geographic coordinates to the projected coordinates, which is the process also called the projection, and also transferring from one type of coordinate system, it can be our geographic coordinate system or projected coordinate system, the map stored in, to the same type of the coordinate system. The process is called reprojection, and it involves several mathematical processes. So here is the diagram, the process of how the reprojection is done. For instance, you have the map, or for instance a point which has x, y, z coordinates, right? Like this. And this coordinates is reference to the coordinate system. For example, the ETRS-89, which is and this coordinate reference system is comprised of the datum, which is a mathematical model of the Earth. It's a certain type of the ellipsoid. For instance, ETRS-89, and the coordinate system, which also has the XYZ coordinates. So coordinate reference system is comprised of the mathematical model of Earth, the datum, right, and the coordinate system. And when we transfer the one from one coordinate system map to the other We also make several mathematical operations. First, we define the datum on which the coordinate system is based, right? For instance, VGS84, and also coordinate system itself. And thus we make a new coordinate reference system. For instance, mostly the coordinate reference system has the names of the datums, and which and we transfer the XYZ values of the point, or the just the one map, to the other values which defines the location of a map. So the process is called reprojection, and in our module, in our tutorial, we will work both with the projection and reprojection processes. So this is how the several types of projections influence to the representation of a map. In our case, the map of the USA. The first, the left bottom map is of the USA, it belongs to Mercator type of projection. The reference coordinate system is EPSG, right? This one, and this is the other type of projection. I think it's towards the area, or probably the direction of the map, and the coordinate reference system is EPSG. I think this is the datum, and this is the name of the coordinate reference system. And this one is the equal. This is actually the equal area projection. It's towards the direction. It's this map. This maps towards the area. And the last one, I think it's towards the distance between one point and the other, for instance. So it depends from the goal of your projection. It depends what type of projection you choose. For instance, you want to measure the distance between two points, right? Two cities. Measure it accurately. You should choose the equidistant type of projection to preserve the distance between points. But for instance, you're going to calculate the exact area of the countries or the regions. You should always choose the equal area type of projection. So on this slide I stop this video, and let's start our practical.